first really major breakthrough was Fourier's breakthrough, came in 1807, in which he was studying, heat flow on various solid bodies. And his big observation there was the thing that we now call Fourier's trick, which is that if you have a Fourier series, if you have a function and it is expressible as a Fourier series, and here I'm going to use complex exponentials for my Fourier series. So this is my trigonometric function. If your function f can be expressed as some coefficients times trigonometric polynomials, then Fourier's trick is that it must be, this coefficient f hat n must be given by the integral here. The t is the torus, so you can just think of it as the interval 0, 1. It must be given by integrating the function against the sort of conjugate exponential, right? And now, so nowadays we have language to talk about what's going on here, and the language that we would use is orthogonality, right? That these trigonometric polynomials are an orthonormal basis of L2. That's not something that was at Fourier's disposal at the time, but he sort of had the observation that there was something of this nature going on. And very quickly after Fourier's sort of observation, it became clear that sort of logically, the question of Fourier series had been reduced to a question of, well, if you just define the coefficients in this way, what can you say about this series, right? There's no longer any question about what these coefficients might be. They're uniquely specified. And so we don't even really think about what they might be anymore. We just define them in this way. And then we ask questions about whether or not this series converges, okay? So this is a story that we see in a lot of like undergraduate analysis classes. We talk about some level of Fourier series, and it's a familiar story, I think, for most people. When you're talking about this series and wondering whether or not it converges, the first question that you have to sort of address is, well, what do you mean by infinite series, right? And usually what we do is we take this infinite series, right? So it's not entirely trivial, right? Because you have an infinite series, it's doubly infinite. And so you have sums, say, from n equals minus infinity to infinity. And usually what we do is we just replace this with what we call a symmetric partial sum, which is where we take the series and we cut it off from minus capital N to plus capital N. And then we take a limit. Okay, and this is the canonical thing to do. This is not the only thing that you can do to understand what this expression might mean, but it's a rather natural thing to do. And when you do that, there are a lot of really great theorems that you can prove that are not too difficult. One of the sort of first ones that people usually see in an analysis class is that if you have a function and that function has a point of differentiability, then the symmetric partial sums converge to the function at that point, okay? Another sort of famous one is the Riesz-Fischer theorem, which tells us that if you interpret these partial sums of this Fourier series in a Hilbert space setting, then the partial sums converge in the Hilbert space L2 norm, okay? These are both like fairly sort of accessible results, okay? There are also some other things that you can prove, much more sophisticated things about pointwise almost everywhere convergence. And those are related to some really celebrated results of the 20th century in harmonic analysis. But I'm not going to talk about those things. What I want to talk about is what happens when you start looking at series with more than one variable, okay? So the idea here is that we now have Fourier coefficients f hat, which are indexed by an n, and now n is going to belong to zd instead of just the integers. And so the trick of symmetric partial sums is not obvious, because when you take this sort of multiply infinite sum and you cut it off, there's not a single canonical way to do that. Okay, because there's sort of too much room to move around in ZD in a way that there wasn't in just the integers. One thing you can do, a natural thing that you might try, is you might say, okay, well, why don't we cut it off on balls, right? So for each capital N, we're going to look at the sort of integer tuples whose norm in the little L2 sense is less than n, okay? And so we can take these balls and as n grows, these balls expand and get larger and larger, and we can take a limit that way, a limit as this radius goes to infinity. So that's a natural thing to do. It's not a thing that we talk about in sort of introductory analysis classes. And the reason that we don't talk about it is that extremely bad things happen if you try this. And in particular, this convergence generally doesn't happen. As you let this capital N tend off to infinity, you don't get convergence in norm in the Lebesgue spaces unless p equals 2. That's the only time that you get norm convergence. And you also don't get pointwise convergence almost everywhere for p's in the range 1 less than or equal to p less than 2. So this is really, really strange. It's not something that people expected. And this goes back to work of Pfefferman in the sort of mid 20th century when he was an introductory graduate student. He proved a result that said basically there's this object called the ball multiplier, and he proved that the ball multiplier was unbounded except on L2. And this was really, really shocking, and it really kind of unraveled the sort of the worldview at the time. People sort of expected that it should be basically simple, that sort of higher dimensional Fourier series should work in basically the same way as 1D Fourier series. They were really, really not expecting this complete sort of upheaval and this major difference between 1D and higher dimensions, right? Because even D equals 2 is immediately a problem. So what are you supposed to do? Well, this is a slide which I included. I'm not going to talk about it, but I'll sort of, since we're being recorded, if you want to go back to the recording and pause it and you can read this slide. This is basically a sort of very brief explanation of how we get this result in the red box from the previous slide, basically just using kind of functional analysis type arguments. All right, so anyway, I'm going to skip that part. So this leads us to the sort of area of mathematics that we call Fourier restriction. Okay, so one thing that happens when you're sort of working with Fourier series, and it's a thing that you can also observe in one dimension, is that Fourier series really don't like it when you treat them harshly, right? And by treat them harshly, what I mean is do exactly this thing where you take the whole infinite series and you do a rigid cutoff where you include all the terms inside some range and you just completely throw away the terms outside the range. And one way that we can treat a Fourier series more gently is to, instead of just sort of having all in or all out, we can include a weight factor. And the idea is that this weight factor here is going to be 1 or very, very close to 1 when your sort of integer n is very small relative to how big your whole interval is, right? And then as this n grows, this weight factor very gradually decays, okay? So the point is that we are going to, instead of just including or excluding this term, we are going to gradually reduce its effect as we go further and further out, okay? So there's something smoother here than just a rough cutoff. And we see this in an undergraduate analysis context, in the context of the Cesaro means of the Fourier series. So what this is we take the symmetric partial sums and we average them. And on the sort of Fourier side, this corresponds to exactly what I just described, taking a weight and sort of gradually changing the weight from 1 at the middle to 0 at the outside. And this thing in 1D, this thing behaves much better than the actual partial sums. It converges to the function at any point of continuity. That's not true for the symmetric partial sums. You can come up with continuous functions where the symmetric partial sums diverge at a point, or in fact, lots of points. But these guys have better convergence property. Any point of continuity, you have convergence. In fact, any Lebesgue point. You have norm convergence in LP for any p between 1 and infinity. You have pointwise almost everywhere convergence for basically all LPs. And so things are a lot nicer if you're more gentle. And one sort of saving phenomenon for higher dimensions is that this same thing happens in higher dimensions, which is that if you take that harsh cutoff and you smooth it out, things get a bit better. So in particular, you don't want to just take the ball and say cut off so include all the terms in the ball and exclude all the terms outside the ball. But what you want to do is you want to include a weight factor just like this one. That's a function of the radius. And you want it to be 1 at radius 0 and smoothly sort of vary down to 0 at radius n, and use something like this, okay? And it turns out that if you do a really, really smooth weighting like this, it works great. And you can recover most of the 1D theory. It's not particularly difficult. It's the realm of what we would call Cauldron-Zygmunt theory, which is a very well-developed sort of theory of harmonic analysis. Now, I mean, people being people, there was a natural conjecture which arose in this whole process. And the conjecture was, okay, well, I know that if I'm extremely rough and I just take all terms inside the ball and no terms outside the ball, I know that this is really bad and nothing good happens. I also know that if I'm extremely gentle and I take a, say, infinitely smooth sort of weight function, that things are great. And so, you know, people being people, there arose this sort of question called the Bochner-Ries conjecture, which is basically a technical conjecture about exactly how smooth you need this weight function to be in order to achieve the kind of convergence that you want to have, right? So the idea is that you have a bunch of different sort of Lebesgue spaces that you might want convergence in. And for each P in each dimension, there's a question of, well, exactly what's the minimum amount of smoothness that I need in terms of this weight function in order to get the right kind of norm convergence. And I'm not even going to state the Bochner-Ries conjecture because it's full of all kinds of exponents and things which don't really mean much. They're very sort of well defined and there's a good reason for what they are, but it's not really that meaningful to know what they are. But it's just, but it's useful to know that this conjecture is out there. It's still totally open. Well, except in 2 dimensions, it's sort of been established. But in 3 or more dimensions, it's still basically open. And it's the kind of conjecture in which people make sort of progress, right? So mathematician A makes progress and publishes a paper of size n, and then 5 years later, mathematician B makes half as much progress in twice as much space, and so on, right? So the papers get longer and longer and longer, and the sort of the change in the exponents gets smaller and smaller and smaller because we're getting closer to the result, but it's still not there, all right? So this is the thing. So this Bochner-Ries conjecture was an animating sort of force behind harmonic analysis in the mid 20th century and still today. All right. So now we get to the geometry side of it, right? Because the idea was this. So you've got this kind of complicated conjecture about exactly how much smoothness you need in this radial cutoff type situation. And a natural thing to do when you're talking about radial cutoffs is to use polar coordinates, right? So what ended up happening is mathematicians, including Stein, started thinking about what happens if you do the following thing. So we're going to take a function f, okay? This is going to be some function on Rd. Okay, and then we're going to take its Fourier transform. Okay, it turns out that there's not really a distinction here between Fourier series and Fourier transform, and it's a little bit nicer to work on sort of Rd instead of the d-dimensional torus. So this is what we do, okay? And then what we're going to try to sort of think about what happens if I take this Fourier transform and I apply some kind of smooth weighted cutoff here. And so the natural thing to do is to take this Fourier transform and try to restrict it to spheres of constant radius. So let's think about the canonical example of restricting it to the unit sphere in Rd. Okay. Now, this is whether or not this can be done. Take a general function, take its Fourier transform, and then restrict it to the unit sphere. Whether or not this can actually be done is actually an extremely delicate question because we're talking about sort of measure theory in the background, right? And so in particular, when you have functions and we think about them in a measure theoretic way, functions are not really defined on sets of measure 0, right? Because we have the equivalence of functions modulo equality almost everywhere. And so for general functions, if you take a function on Rd and you restrict it to the unit sphere in the sort of analysis world, you can't really do that, okay? Because there's no there, right? However, we're not just taking a function and restricting it to the unit sphere, we're taking the Fourier transform in between, okay? And there's a phenomenon which comes to the rescue, which is that, for example, if your function happened to be integrable, right, then we can show without too much difficulty that actually the Fourier transform of f is actually continuous. Okay, and because we're talking about measure theory, what that really means is you can redefine it on a set of measures 0 to make it continuous everywhere, right? But so the point is that for an L1 function, for example, actually you can talk about what the pointwise values of the Fourier transform are. And so once it's continuous, restricting it to the unit sphere is trivial, okay? So if you have a function in L1, life is really great. So this is the good situation, okay? There's a bad situation, which is that if f is in L2, then what do we know about the Fourier transform of f? Well, on L2, right, this is a Hilbert space. We know that, we know by Plancherel's theorem, right, that actually the Fourier transform is an isometry on L2. It maps it to itself, okay? And so in L2, f hat could in principle be any L2 function. Any given L2 function, right? Because take any L2 function that you want, take its inverse Fourier transform, it has one. It's another L2 function, you go forward and there you are, right? And since L2 functions are sort of genuinely measure theoretic quantities, you cannot define them on sets of measure 0. So this makes no sense on sets of measure 0. Okay, and so there are these two sort of extreme cases. L1, life is great, things are easy. L2, it's impossible. It's not the case that people haven't worked hard enough. It's just that it can't be done. Okay, and so what Stein found and some others as well was that there's actually a sort of transition that's for some p's that in some cases for some p's bigger than 1 you can still accomplish this restriction. But if the p's are close enough to 2, then you can't. And there's a weird transition point where below that transition region, it's possible, and above that transition point, it's not possible, okay? And in fact, sort of Stein was the and Thomas together proved the first real theorem of this sort. And there's an exponent about what kind of p's you can take. And this is the, this is sort of the opening line in a story of its own, but they sort of observed, there's this sort of transition thing that happens, and you can sometimes restrict the function to the unit sphere for appropriate values of p, okay? Now, so they did this for the unit sphere in RD. It turns out that if you try to restrict to something else, if you try to, for example, restrict to a hyperplane, an affine hyperplane, it's really easy to write down counterexamples that show that no non-trivial inequalities can be true, right? So we know that L1 always works. If you try to restrict to a hyperplane, you can show that L1 is the only thing that could possibly work. And so there's something fundamentally different about the unit sphere and an affine hyperplane. And the question that I want to talk about is, what is it? What's the difference? What matters? Okay, geometrically, there's something going on. And it's not too hard to guess that maybe it has something to do with curvature, right? Because the thing about a sphere is that a sphere has curvature and a hyperplane doesn't, right? So the real question is, how do we quantify what matters? Okay, so there were some efforts to sort of think about what this means. It turns out that the question is a lot easier if you talk about manifolds of codimension 1 or curves. That in these two extreme cases, it's easiest to see what's going on. Now in intermediate situations, it becomes much more complicated. So one thing which you can do right off the bat is you can think about what are the symmetries of this problem. It turns out that the symmetries matter quite a lot, okay? And one really, really important symmetry is affine invariance of this problem. So I should really probably say equiaffine invariance if I want to be really technical about it. So the idea is that I'm going to take RD and I'm going to sort of act on it by some kind of affine linear map with determinant 1. Why do I want determinant 1 here? Well, because I'm an analyst and I care about measure. And maps with determinant 1 preserve measure, okay? So this is some kind of affine transformation that preserves measure. It's fairly easy to check that if you take this affine transformation and you go back to that sort of Fourier restriction type inequality that I had before, right? Where you're going to take some submanifold, you're going to take a Fourier transform, you're going to restrict it to a submanifold. And you're going to ask, well, does this belong to LQ of the submanifold? And when I say belong, I really mean in a continuous way. Is there some kind of continuity property? Right? So what you can do is you can take this manifold here and you can act on it by this affine transformation. So what I mean, for example, is if this sigma is your unit sphere, I mean, think about ellipsoids instead, okay? So we're going to think about ellipsoids instead, and you can sort of check, it's just sort of chasing constants that if you knew a Fourier restriction inequality for a sphere, it turns out that a Fourier restriction inequality for an ellipsoid has to also be true. And actually the constant here has to be exactly the same. It can't even be different. They have to be just exactly the same. And that's just because if you take functions in LP and you act on them by affine transformations, they still belong to LP and their LP norm is still the same, right? And so one way that you could sort of realize transforming sigma is by applying essentially an inverse transform to the functions instead, right? And so you don't really have to, you can always write a restriction to an ellipsoid as a restriction to a sphere of some adjusted function, okay? So this suggests trying something, which is that instead of, so when you are looking for one of these sort of Fourier restriction inequalities, instead of just looking for like sort of simple functions to test it on. So one thing which happens almost all the time when you're talking about functional inequalities like this is you test them on simple functions, like functions that are characteristic functions of balls or something like that for various radius and various positions, and you see what happens, right? So what we should do is not just test it on balls, but we should actually test it on all ellipsoids, because the ellipsoid should work the same way as actual balls do too, okay? And it turns out that this is sort of a really reasonable idea, and sort of Oberlin, so this is Dan Oberlin from sort of FSU, had this observation that if you have a measure on a manifold and it satisfies a Fourier restriction inequality, then it just so happens that you can write down a condition that the measure of any, in fact, convex set. So now this is a measure, this is like Lebesgue measure on the unit sphere, for example, okay? And I'm going to take this measure on the unit sphere, and I'm going to sort of take compact convex subsets of RD and see how big does the unit sphere measure think that they are, right? So the idea is that I have my measure here, and then I have, say, some convex set that looks like this, okay? And what I'm going to do is I'm going to ask the question of how, you know, how much in this case, since it's a 2D problem, this is arc length, right? So the question is, what is the arc length of this white segment? That's what mu of k is. And absolute value of k is the volume of the set k, okay? And so what happens is there's a relationship between how much arc length sits here and how much volume this triangle has, okay? And in particular, the total amount of arc length is bounded above by some power of the volume. And what that means is, in fact, if you took a set here which was degenerate, a set which had volume 0, then it wouldn't intersect this circle in any positive arc length at all, right? And you can see why that is, right? It's because if you take a set which has a convex set which has no volume, it's a line segment, and the circle doesn't contain any line segments, right? So the best you can do is just kind of glance off it, but it's still sort of length 0, that intersection, just a single point, right? So this is now a sort of very geometric measure theory kind of question. So the question is, okay, I have a measure on some sort of submanifold, and it has this property that, you know, if you sort of want to know how big the intersection is with a convex set, it's controlled by a constant times the power of the regular sort of volume of that set. And the question is, well, what do these things look like? Because this is a necessary condition for any Fourier restriction inequality to hold. Okay. So this is the same definition from the previous slide. The question is, well, yeah, what are these measures? So in 2000, Dan Oberlin actually characterized what these measures kind of look like, or in particular, given a manifold, what's the best possible measure on that manifold that satisfies such an inequality? Okay, so he did it for particular exponents. Because these are the ones that sort of turn out to be the most interesting ones analytically. And it turns out that the measures here that work really, really well are known, okay? On curves, so if gamma is a curve and you want to put a measure on a curve which satisfies this kind of inequality, the measure that you should put on it is called affine arc length, okay? And what you do, there's an easy way to describe how you compute affine arc length. And that is you give me a parametrization, right? So gamma is a parametrization of the curve. And what I'm going to do is I'm going to look at the first, second, third, up through n plus first derivatives of this parametrization, treat them like sort of column vectors, stick them together into a matrix, take its determinant, and then put it to a certain power, and then integrate against that, okay? Now this looks like a really weird thing to do. But it's really, really nice. And the reason that it's really nice is that it's got a whole bunch of sort of geometric invariance properties. Like among other things, even though it looks like it depends on, the parameterization, it does not, right? So it's pretty easy to check that this measure is actually independent of the parameterization, okay? And the reason is that, you know, even though it involves higher derivatives, when you start talking about, if you took this parameterization and you composed it with a change of variables, these guys would be really complicated and they would be all kinds of junk terms, but the junk terms would be linearly dependent on the previous rows. And so actually they cancel out, okay? And this factor here is exactly carefully chosen so that the factor that comes out at the end is exactly the factor that you get when you use the change of variables formula or something like that, okay? So it's completely independent of the parameterization. It's also independent of affine transformations of the curve itself. So if you change Rn in an affine way that preserves sort of measure in Rn, then you get the same measure out, okay? There's another one at the other end of the spectrum. It's called the equiaffine hypersurface measure. And basically what you do for this one is if you've got your hypersurface written as a graph, you can basically take your measure to be some power of Gaussian curvature times sort of the regular Lebesgue measure on this. Okay, so this is the Hessian matrix of second derivatives. So these are sort of very classical things. You can sort of find literature about these measures going way, way, way back. But there's a gap, right? So I can tell you everything there is to know about curves and everything there is to know about hypersurfaces. But in the middle, there's really no, I mean, sort of prior to this sort of recent work, there was really nothing sort of known about what the right object even was geometrically. Okay. So Oberlin also sort of had this very interesting construction, which was that you can kind of generalize the classical Hausdorff measure in this affine way. And the way that it works is that you take your set E. So for usual Hausdorff measure, you take your set E, you cover it by sets, right? And then you sum up some power of the diameter of those sets. And then you try to make that as small as possible, basically, subject to constraints that you have to make the set small. So Oberlin's idea was you do something similar. So you take your set E, you cover it by, let's say, convex sets. But instead of summing some power of the diameter, let's sum some power of the volume. Now in 1D, this is no different, right? In 1D, it's exactly the same. In higher dimensions, it's entirely different, right? because you can have sets of large diameter with no volume in R2, okay? And so this measures something entirely different. And so this is, so any kind of an object that satisfies the Oberlin affine curvature condition is going to naturally give you one of these kind of affine Hausdorff measures. And the question is, again, what is it? How does it relate to the regular Hausdorff measure? Okay, so so the theorem is there's a way to compute it, okay? That we can say what this affine measure actually is. And just like affine arc length and affine hypersurface measure, there's a geometric way to construct it. And by that, I mean, there's some expression involving partial derivatives of a parametrization. You put it together and you do some kind of cooking up of some formula, and you can write down what it is, okay? And it turns out that a theorem like Oberlin's theorem is true, which is that once you write down this cooked up expression under some sort of general sort of multiplicity type conditions, this, this formula gives you the affine Hausdorff measure, okay? Now I'm not gonna write down what the actual formula is because the real problem in the theorem was to figure out how to even express it, right? It's like, there is no simple, easy way to actually write down what the formula is. What was actually proved was that there is a formula that exists, right? That there is some expression that could be used to do this. And so now we're sort of getting very much into the realm of geometric invariant theory because things become incredibly complicated and it's difficult to be explicit about what you're doing, okay? So, so there's a key sort of piece to this, which is that one needs an abstract way to take multilinear functionals and come up with measures, okay? And so we're gonna do something fairly naive, okay? And so that is, so suppose that A is just some kind of multilinear functional. So you've got, say, vectors in some vector space V, and you've got some multilinear functional in this vector space. I really wanna come up with a measure on this vector space. And so the way that I'm gonna do that is I'm gonna sort of define a density on V. And by that, I'd say if you give me D vectors, I'm gonna take these vectors and plug in copies of these D vectors into A. But I'm also gonna act on them by a sort of determinant preserving matrix. And so I'm gonna take these vectors, I'm gonna transform them in any way that I see fit first, and then I'm gonna test them on A. And I'm gonna take a little L2 norm here, right? Which is basically saying, I'm gonna measure the overall size of these numbers. And so I wanna know what's the overall size of these numbers. And I'm gonna get some answer, but then I'm also gonna say, well, obviously there are gonna be some really crazy choices of matrix which make these numbers really, really big. That's not really what you worry about. You worry about what happens if the numbers are all really, really small. And so you have to take an infimum instead, okay? So you do this weird sort of calculation and it turns out it gives you a density. And by density, I literally mean it has the kind of transformation law that you would expect, which is that if you put in some matrices T here, you can sort of forget the T at the cost of not determinant of T, but absolute value of determinant of T, okay? So this is just some abstract construction. It turns out that this is a really interesting thing, and it's a thing which I think in analysis is fairly foreign, and in sort of the area of geometric invariant theory, it's something that's pretty familiar. Okay, so one should recognize. So if you are sort of familiar with that literature, I wasn't. So I'm not going to assume that you were for your whole life because I wasn't until recently. But this object is an object that one encounters in Kempf-Ness theory, for example, right? So we have some vectors. We're looking at an orbit with respect to this with this group, and we're looking for a minimum norm. Okay, so this is a thing which has some algebraic significance, but what wasn't clear is that it also has analytical significance as well. Okay, so I'm going to give you a really concrete example of why one would do this, right? So suppose that you had a bilinear form on a vector space, right? So you're just living in some world where you have a bilinear form and you're not really sure what to do with that bilinear form. You're a geometer, somebody hands you a bilinear form, you think it's really interesting, but you don't really know what to do with it, right? So one thing you can do is you can create one of these densities like this, like the previous slide. And so what we should do is you should give me a d-tuple of vectors. And what I'm going to do is I'm going to sort of regard these v1 through vd as a basis of the vector space V. I'm going to really write the matrix of G in that basis, but I'm also going to change the basis by some m, which has got determinant 1. And so what I'm going to basically do is I'm going to sort of think about this G, write it in all these possible bases, and think about the sort of the size of the matrix entries, okay? And I'm going to take an infimum here. Now, if you're a little bit clever, you can sort of write this out in a specific way, and you can understand that this is going to be the trace of something, and you can use the arithmetic geometric mean inequality to say that the trace of this symmetric matrix is bounded below by some power of the determinant with a constant. And when the dust settles, it turns out you can actually do this calculation explicitly for a matrix. And this density that you get is going to be some constant, which is in fact d to the power d over 4, times the square root of the determinant of G. Okay. Now, that should be something that's familiar, right? Like in Riemann geometry, when you have a bilinear form, which is the metric tensor, right? And you want to integrate on a Riemannian manifold, you take square root det G as the volume form here, right? And so the point is that even if you didn't know that's what you were supposed to do, if you had this other sort of process in mind, it would naturally lead you to thinking about that as being the right measure, okay? And so you can really think about this in the following way, which I think is really kind of useful. You can think about this as something like the sort of the greatest dream of every linear algebra student, which is that you have some really big matrix, right? And you want to know if its determinant is 0 or not. And the bad news is that it's not that easy to tell if a matrix has determinant 0 or not, especially if it's a really large matrix like 20 by 20 or something. It would be really, really nice if you could just tell by looking, right? It would be really, really nice if you could just say, oh, well, you know, there are some big entries in that matrix, and so the determinant won't be 0. Look, that entry, that 4, 4 entry is 100, and so it's not determinant 0, right? Like, that's unfortunately not true. But what is true is that if you sort of find the coordinate system which minimizes the norm squared of the entries, then that's true, right? That if there is no coordinate system in which the entries are all less than 1, then the determinant is not 0. So there's this sort of you know, trade-off, which is that you can be a little bit lazier and just look at magnitude of coefficients at the expense of having to recognize that you might need to change coordinates. Okay, so this is a sort of simple but rather deep thing. Okay, so now I want to tell you, on the basis of this observation, I want to tell you how you compute this measure that's sort of sitting in the background. Okay, and so what I want you to do is take your, so you've got Rn, you've got a d-dimensional submanifold of Rn. Okay. What I want you to do is I want you to give me a parametrization of your submanifold. And it's really, I mean, this is really a local construction. So you can really just think about it as being on RD or some sort of little piece of RD. Okay. And so now what I want you to do is I want you to take this map and I want you to start differentiating it by vector fields. Okay. So it's d-dimensional. And so there are d different directions that you might differentiate in. Okay, so I want you to differentiate in the first direction, second direction, up to the d direction. Okay, then once you sort of run out of directions, I want you to start doing second derivatives. Okay, so put together all the pairs of second derivatives that you can until you run out of second derivatives, and then start using third derivatives and put as many third derivatives as you can until you run out. And by run out, I mean encounter one which would necessarily be linearly dependent on the previous ones. Right, because we're going to take a determinant, and so you absolutely don't want things to be linearly dependent in here if they don't have to be. So you take as many second derivatives as you can, then as many third derivatives as you can, and then you finally stop when the number of columns that you've built is equal to little n, right? Because then you get a square matrix. Okay, so you take this thing, you start taking. So look, it's a lot like the affine arc length construction, right? Because if this were a curve, there would really only be one direction. And so that you would take one first derivative, then one second derivative, and one third derivative. And you just keep taking one of each until you got the number of columns that you needed. So here you just take as many as you have of each type until you get to the end. And now we have a multilinear functional. From this multilinear functional, you can construct a measure using that formula / rule from a couple of slides ago. And it turns out that that is the right thing. Whatever that weird measure is that's built on this tensor, it gives you the best possible measure for the Oberlin affine curvature condition. It gives you a measure which is invariant of parameterization. It's also got affine invariance and the space Rn. And so this is really some geometric object, right? It's something that's got a bunch of geometric invariance. So it's an interesting and important thing. Now there's sort of a next layer of this story. So I'm not going to talk really about how you prove any of that stuff because it gets to be messy really fast. But that's kind of the geometric situation. There's a sort of a related problem in harmonic analysis in which you're not trying to quantify curvature, you're trying to quantify transversality, right? And it turns out that these things are actually pretty closely related because in some sense, from the problems of Fourier analysis that rely on geometry, many of them can be understood in the following way. If you need curvature, one way you can identify curvature is to look at the sort of tangent spaces of nearby points and check to see whether you have some kind of transversality, right? So the picture is that, like, if you want to know whether or not there's curvature of the circle, what you should do is you should take that tangent space and that tangent space, and you should look to see whether or not they're transverse. And in fact, they are, right? Because in this 2D case, we have a pretty clear sense of what transverse should mean. And so the fact that these two lines intersect in a sort of non-trivial way is telling us that there's some curvature here. So quantifying transversality is an important question. Analytically, the specific way that we usually want to measure transversality is in terms of this very specific multilinear inequality. So let me sort of say what the various parts are. So here we have a bunch of linear maps, pi j, that go from some RD to RDJ, and they're surjective. And you have some number of them. It doesn't really matter what. Then you have for each of these, you have an exponent. And what we're going to do is we're going to take functions that live on the RDJs. We're going to compose them with projections, take some power of each one, multiply them together, and integrate. And the question is, what's the best possible constant such that this crazy thing is less than or equal to this finite constant, hopefully finite, times the product of the L1 norms of the individual functions raised to the right power pj. Now this is a really, really, I mean, written at this level of generality, it probably looks like not much. But one should recognize that basically all of the classical inequalities in analysis can be written in this form. Okay, so for example, you could have like Holder's inequality, right? Which would be where D is equal to D1 and D2, and my projection is just going to be pi j of x equals x, right? So I would have f1 of x raised to some power p1 and f2 of x raised to some power p2, and I want to integrate that dx. And I want to know what's the best constant here, such that this is less than the product of integral of f1. Well, I don't need a product, I guess I'll just write integral of f1 times integral of f2. Okay, and remember that p is between 0 and 1, and so it's really the reciprocal of the exponents as we usually think of them. Okay, and so what I really want to do is I want to now really sort of replace f1 with, say, g1 to the power 1 over p1, and replace f2 with g2 to the power 1 over p2. And then we're asking the question G1, G2 less than or equal to constant integral of G1. And let's give 1 over P1 the name Q and 1 over P2 the name Q1 and then Q2. Then we're looking at right? That's the question. So this is the sort of classical Holder's inequality. And the question is, what are the exponents? Well, we know that there are some exponents for which it's true and some for which it's not. And so this is an example of a Braskamp-Leib inequality. Young's convolution inequality is also a Braskamp-Leib inequality. Like basically most sort of basic inequalities in analysis that you can think of are one of these things. Of course, you can also write down plenty of them where the constant isn't finite. And so the question becomes, well, how do you know whether or not this constant is finite? If you just give me some data, if you give me some projections and some exponents, how can I tell whether or not this, this constant here will end up being finite or not, okay? So Leib in the 70s proved that there's a really simple way to, well, simple in some sense, way to understand whether or not the constant is finite. And that is, all you have to do is plug in Gaussian functions for the FJs. That if the inequality is true for all possible Gaussians, FJ, then the inequality is true for all functions, okay? And so what this means is, so bottom line is we can take this inequality here, we can just plug in Gaussians, and then we have to sort of figure out what the constant is. It turns out that, again, there's a geometric invariant theory way of doing this. So I will sort of spare you sort of the details because I'm running basically out of time. But the bottom line is that there is, again, a multilinear sort of functional such that the Braskamp-Leib constant's reciprocal can be written as, well, you take this multilinear functional, you look at its orbit under the action of some group, you take its norm and you take its infimum. Okay, so this is exactly the same kind of construction that we had before in constructing that measure, right? So you take some object, you sort of act on it by a bunch of matrices, you look at the norms, and then you find the sort of collection that gives you the smallest thing, okay? And this is an exact equality, and in fact, the constant can be explicitly computed too, okay? And so it means that this abstract algebraic or abstract analytic thing, this norm, can be understood in an algebraic way. And there's a whole, this sort of opens the door to a whole bunch of things, which I don't really have time to talk about. But it means that there exist polynomials that you can use to sort of test whether or not a certain collection of data is going to give you a good constant or a bad constant. And it like really collides worlds in a way that's really strange. All right. So yeah, so the reason this matters is that, well, the idea is that now we're going to think about, instead of, we're going to go back to the situation where I have like a submanifold, for example, and I'm going to take that submanifold, and for each point on the submanifold, I'm going to attach to it surjective map here. So this map you can think of as encoding the tangent space, right? And so what we want to do is we want to say, okay, so I'm going to take my submanifold, I'm going to encode the tangent space, and I get a bunch of these maps. And then the question is, well, are they transverse in the Braskamp-Leib sense? And once again, the answer is, well, there is a way to sort of determine whether or not this is true. And this is kind of a generalization of the Oberlin affine curvature condition, okay? Because what we had before was we were sort of talking about the measure of a set being controlled by a power of the volume. So now we're asking, can the measure of the set be controlled by some kind of transversality quantity? Okay, and I say it generalizes the Oberlin affine curvature condition because for a certain setup, you can actually recover the Oberlin affine curvature condition as being one of these guys. Okay, there's a lot more to the story, but that's kind of where I think I should probably stop. So what's next? So it's really interesting that all of these sort of objects start appearing in vastly different literatures, right? So I would never have imagined. I mean, so when I was in graduate school, these were still the days when you had to pass foreign language exams, right? That you had to. I had to pass a reading exam in German and a reading exam in French, and I worked really, really hard for the German exam and passed it, and realized that they weren't holding us to a very high standard, and so I did not work very hard on the French exam, and essentially sort of scraped by, but nearly failed it. But actually to use it, because I actually had to read a paper from the 19th century written by Hilbert in German to sort of understand the sort of the geometric invariant theory of his day and how it sort of relates to the kinds of analytic objects that I've talked about now. So it's a strange thing. And it's also strange because it's at the intersection of these different areas. And so it's not exactly what any one area is traditionally used to studying, right? So we're talking about geometric invariant theory, but not the kind of quantities that are sort of generally well studied in that literature, because we need to do something a little bit different. And we're talking about analysis, but it's the kind of analysis that's involving all kinds of tools that one doesn't usually use. And so there are a lot of really interesting, really basic questions that are just not, that there's just not much that one can be said about them because nobody's really thought about them. So it's really kind of interesting that the geometric invariant theory sort of side of things can say something about the Braskamp-Leib constant, because it turns out that the Braskamp-Leib constant is actually really, really important in a lot of situations. I would be lying if I said I understood what it was, but I know that in computer science, the magnitude of the Braskamp-Leib constant is really, really important. So much so that they develop algorithms for actually trying to approximate it. Like they need to know actually what it actually is. And so there's some really meaningful sort of information that comes from this sort of cross-pollination. One thing which I think is clearly missing is that when one moves into this world and starts seeing these objects, as an analyst anyway, I can say, when you start seeing these objects, you really come to appreciate how well developed the theory of linear algebra is and how relatively undeveloped the theory of multilinear algebra is in comparison, right? Like you have all these great algorithms for knowing whether a determinant is non-zero by doing row reduction and all these things and all this kind of stuff. In geometric invariant theory, it would be really, really nice to have really explicit computational tools. And when I say really explicit, I mean ones that can be done by hand, right? So it's always, I mean, there are a lot of there exists statements that one can do such and such and such and such, but computationally it becomes so difficult that it's not a sort of hand calculation in interesting cases that are coming up from the analysis side. And so it would be really nice to understand what multilinear algebra really is, if there is such a thing. And then it's just sort of an interesting thing is that in analysis, we don't really care if the exponents are rational or irrational. But in the geometric invariant theory setting, one really only sort of understands what's going on when those are rational exponents. So the question is, could you go backwards? Like, could you have something meaningful to contribute to the sort of geometric invariant theory side of things by using the fact that in analysis we have sort of some spaces that we move in that weren't previously available. So I think that's a good place to stop. So thank you very much for your attention.
Thank you, Phil, for a very nice talk and an epic and whimsical description of Fourier restriction. I appreciated that. So let me start by asking if anyone has questions before I ask a question.
Can I ask a silly question? Mm-hmm. In that Pfefferman result, in the case when your indices are laying in some rectangle, everything is okay, isn't it?
Yes, that's right.
Which means if you'll go for some infinite strips, which is everything is blowing up, and then for, let's call radiuses, it's blowing up outside of P equal 2, yes?
Yeah, exactly. So the Pfefferman result is interesting because in the Pfefferman result, flatness is actually good. And on these other situations, the flatness is bad. And that's kind of a strange, it's kind of a strange reversal.
Yes, as I just wrote some paper when I was just hit by this, yes, and I didn't get any kind of understanding why summing squares is going to blow up when small L1, it's okay.
Yeah, exactly. It was, I mean, it was really, my understanding of the situation was that it was really earth shattering, that people were absolutely not expecting that at all.
And then one other thing, when you mention about that S dimension affinite Hausdorff measure, it somehow reminds me something like entropy numbers. Is there any relation with that or not at all?
So I can't say that there's no relation, but there's not any that I'm aware of.
Anyone else would like to ask a question? So Phil, you mentioned this idea of quantifying transversality, which is interesting to me. Does that come up in your own work somehow?
Yeah, so it's I didn't think that I would get further than this, but it turns out I planned for it. So in my own work, I'm sort of thinking about various kinds of operators where you integrate over submanifolds. And it turns out that there's a natural sort of important inequality that's related to this, where the Braskamp-Lieb constant actually shows up, right? And so you have this inequality, you need to understand how to use it. And that means you need to understand how big the Braskamp-Lieb constant actually is. And so by quantifying transversality, what I mean in a sort of technical sense is, I mean, knowing how big the Braskamp-Lieb constant is. And so you need some kind of tools to be able to work with this. And that's how I got into all of this stuff, is like encountering this thing and then recognizing that that there's some significant need for sort of not just, but you need to understand this constant really, really well, not just in terms of the analysis, but in terms of the algebra as well.
Thank you. Well, if there are no other questions, then I on the count of three,
it looks like we might have one.
Oh, one more, please.
Hi. I was wondering, actually, with your further directions and stuff, you were talking about understanding, I guess, multilinear algebra with what happens when we get into higher dimensions. And I was sitting here laughing because I spent a little time trying to dive into what is actually out there for that when I was trying to improve some decay bounds and thinking about higher dimensional Taylor series and trying to actually understand that in a usable sense. So I was curious if that's anything you've actually given more thought to, or just
Yeah, I've thought about it a ton, right? Because it would be so useful to me to sort of have some kind of just really basic toolbox for how one works with these kind of multilinear objects. And I've looked around, and I mean, there's a lot of stuff out there, but I think it's like basically the stuff that I found was everybody was developing just exactly the thing that they needed. And there's not, and none of it was really the right thing for me. And so, yeah, I thought about it a lot. I have some ideas. I mean, the geometric invariant theory is out there, right? And so it says things, but you're right. I think I have the same experience that you did, right? Which is that, like, it's not just that I need it to be there, but I need to figure out how to actually make it a tool, right? And like, that's really, really hard. And like, I have made some progress in that direction, but not a significant amount.
Yeah, I'd love to figure out some way to actually make it usable to understand when they might look a certain way to set some restrictions. Because I feel like if I could just understand this a little better, I might be able to do something with it.
All right, so if you're willing, let's unmute ourselves so we can give our speaker a round of applause. The sound of
and
a few hands.
Can I ask one more question?
Oh, please.
Sorry for this. I'm looking at all this, unfortunately, only from the point of view of function analysis, yes? And when you mention, of course, in that case, that was called when function f is from L1, that of course Fourier coefficients are continuous. When it's from L2, Fourier coefficients are L2 and so on. When you are looking at that map from LP space to corresponding, let's call, image of that in the LP prime space, LP prime, yes. This mapping is strictly singular if the P is different from 2, isn't it? Which is going to tell you something about quality of this mapping, yes?
Yes, that's true, right? And so what it means,
which means this is in some sense nice. When the P is 2, it's simply identity.
Yeah.
But outside of that is non-compact, but it's nice because it's finitely strictly singular, yes? Which means there is some beautiful inside structure when you are going for invertibility. Is this going to help you?
That's a really good question. I don't really think that anyone has, I mean, not that, as far as I know, no one has really understood exactly what the structure of that Fourier transform map is in the way that you're describing it, right? I think that because really what you're saying is if you take you're talking about like Hausdorff-Young inequality, right? So you take a function in LP and you take its Fourier transform and it belongs to LP prime. But the point is it's not just LP prime, it also has other properties as well. And I don't think anyone really has a good sense of like what the Fourier transform is actually mapping it into. LP prime intersected with what? I don't think anybody really knows that.
No, you just knew, for example, that there is finitely strictly singular, which means you knew that the Bernstein numbers are going to 0, which means there is some, it's non-compact, but there is some nice behavior, yes? It means it's somehow
there's really
nicer.
Yeah.
All right. Thank you, Phil.